Okay everybody, here we are back again, again as always. Any questions, write them down and ask me next time we're in class. And if I make any mistakes, please do let me know. Okay, so we're now looking at mean variance and standard deviation of a probability distribution function. We're still focusing on our discrete variables at the moment, and so let's get started. Now you might remember from previous years we've talked about the measures of centre and measures of spread. So these are two important concepts that we often work with when we're talking about statistics, but they're also relevant in probability as well. Hopefully you've heard of them before and you might have some idea what our measures of centre actually are. So if you already remember some, jot some of them down in your table. Essentially, these are our three measures of centre that we tend to deal with. So mean, as we know, we often refer to this as the average, although that's not quite correct, but it's the sum of values divided by the number of values. That should be something that's familiar to you. Median is, of course, our middle number. Oh, sorry, I can't spell at the moment. Middle number. And the mode is our most common number. So these should be things that you remember from other years when you've been dealing with statistics. We then have our measures of spread, and once again these are things that you will have dealt with before. So if you've got some ideas of different measures of spread, please do list them down yourself. But we should have the range, which of course is our largest minus smallest value. Interquartile range, which we get by taking our third quartile or our upper quartile and subtracting Q1 or our lower quartile. Variance and standard deviation, you may not have heard of these before unless you're studying further maths, but we're going to get onto those a little bit later in this video. Now we can also talk about two other different things that this will need to figure out and discuss later on. Our sample statistics, these are found when our measures of centre and spread are calculated from data, primarily when they're calculated from a given sample of people, a sample of data that we've collected. Our population parameters, on the other hand, are ones that are calculated from the probability distribution. So these are our theoretically true values. So the sample statistics have actually been calculated from data, and our population parameters are the theoretically true values. Right now we're going to be focusing on the population parameters. We are going to come back to sample statistics later on. That will be the very last thing that we will look at before finishing for the year. So let's have a look at this. When we need to calculate the expected value. Now this was originally worked out when people wanted it for gambling, to know what the expected value would be when they work things out. When we read the words expected value, that means the mean. So what we have is the mean, which we use the Greek letter mu to represent, or we can write it as E of x, standing for the expected value of x. The formula for this is that we have the sum of values of our x value multiplied by our probability. Okay, so our sum of values multiplied by the probability. Now, sorry, in the actual formula they don't tend to write the R, so I'll rub that out. So this is what it will actually look like. Okay, so that's our formula, and I'd write that down if I were you. So to calculate the expected value, E of x, or we could use mu, all we do is we add our values together of x times the probability of x. So our first x value is 1, and we multiply it by the probability of getting 1, which is 0.1. Because we're summing, we then add that to, our next value is 2, multiplied by our probability, 0.22, and we continue on. 3 multiplied by its probability, and 4 multiplied by its probability. And that is literally all that we need to do. We put it in our calculator and get an answer. As I have mentioned before, please be aware that sometimes you will need to deal with things like this in the tech-free situation, so you should be able to work this out by hand as well, knowing what we do about multiplying and adding decimals. Continuing on. Okay, let's now look at some properties of the expected value. So the first property that we're going to deal with is if I want to find the expected value of a particular function, what we do is that we first find the value of that function for the particular value of x, then we multiply by the probability, and then we sum these together. So we've got that sum symbol to start with. So if we were to apply this to the first example A here, what we've got is that we need to, our function, our g of x function in this case is x squared. So we need to take our x value and square it. So we're going to have 1 squared, and then we multiply by the corresponding probability, which is 0.1. Plus we then take our second x value, we square it because that's our function inside, then we multiply by the probability, plus continuing on we have 3 squared, our x value squared multiplied by probability, and then our final x value multiplied by its corresponding probability. You work that out. Once again, you can work it out by hand or on your calculator to give us our answer. Now if we're using this in the second case, same idea here. So we've got our function this time is 2 multiplied by x minus 1. So if we took the value 1 and we substituted it in here for x, we'd have 2 times 1 is 2, minus 1 is 1 times the probability. Plus for our next value we take 2 and we sub it in to where the x is. 2 times 2 is 4, minus 1 is 3 times the probability. Continuing on, 3 times 2 is 6, minus 1 is 5. And then we have 4 times 2 is 8, minus 1 is 7. And once again, we can put this in, we can work it out, and we get an answer of 4.5. However, there is actually another way to deal with linear functions, and this is our second property. In this case, we say if we want to find the expected value of a linear function, a shortcut way is that we take our gradient, multiply it by the expected value, and then we add on our constant. So if we're using that in this case here for option B, we would have 2 is our gradient multiplied by the expected value. Now this table here is the same one that we used for example 1 earlier, and if you look back you figured out in that case, well we did together, that the expected value was equal to 2.75. So I substitute 2.75 here, my e of x, plus b is the constant part, which is negative 1. And if we work this out, 2 times 2.75 is 5.5 minus 1, and we get, which is lucky since this is the formula, the same answer as what we had previously. So when we've got linear functions, we can use either of our properties there to simplify and evaluate those expressions. Alright, now we're going to look at our measures of spread. In this case, we deal primarily with variance and standard deviation. Our variance formula is, let me just get a colour that I like, here we go, okay. So there's a few different variance formulas. We tend just to literally use var x to represent variance. What we can do is that we take every x value, we subtract our mean squared, and then we apply our mean formula. An easier way of using this, however, and the one that's easier to work with, is that we use this formula, which is the one that we're going to focus on. So the first one requires you doing lots of individual calculations. The second one requires you to work out the expected value and the expected value of x squared, so it's a little easier. The standard deviation, and this has the best practical application that we can talk about. Standard deviation is the average distance each value is from the mean. So it gives us an idea of how spread out the data is. Now, if we have a nice normal distribution, and this is something we're going to get to later, but it's nicely symmetrical like this. If we have one like this and we have our mean here in the middle, what we end up finding is that within one standard deviation of the mean, so one standard deviation either way, and we use this little sigma symbol for standard deviation, we end up getting 68% of the data. Within two standard deviations of the mean, so we go another one out, we get 95% of the data. However, this is only the case for data that is symmetrical like this one here. For a lot of probability distributions, this is the case, or it's close to this, but when we're not necessarily dealing with a normal distribution, this will not always be the case. And we'll discuss this a little bit more as we progress through. But our formula for standard deviation is quite nice. Our standard deviation, which we can write as SD of x, but the better way of writing it is using the sigma, the Greek letter sigma. That's a straight line at the top, it's not an O, and it's just equal to the square root of the variance. We do have a couple of properties for variance, and we will use these later like we did for the expected value. For now, the main one we're going to focus on, if we've got variance of a linear function, it's equal to just the gradient squared multiplying by the variance of the original values of x. And we will apply that very soon. Okay, so for our particular example here, what we're going to do to start with is to calculate the standard deviation. Now the formula that I recommend, we always start with variance, and I would recommend the best formula to use, the easiest one to use, is this one here. Okay? So what we are doing in this case is that we're working out the expected value first. So for this for part A here, first of all we work out the expected value, or the mean, like we did before. So we take each x value and multiply it by its corresponding probability, and we add together each x value multiplied by the corresponding probability. And once again, you can either put this in your calculator, or if we have to, work it out by hand. Now in our formula, what we're needing is the expected value squared. So we can then square this, which is going to give us 3.2041. To work out the other bit of our formula, e of x squared, this is using the expected value formula from before, the property, where if I have a function inside, I apply this function to each x value first. So I have 0 squared times its matching probability, plus 1 squared times its matching probability, and so on. So this is how we work out x squared, just like before. And once again, calculator or by hand, and we get our answer. So to then work out the variance of x, we need to take our e of x squared value, and we need to subtract our expected value squared value. And we can work this one out as well. Finally, this gives us the variance, but what we're wanting is the standard deviation, which is equal to the square root of the variance, and which will give us 0.75 correct to 2 decimal places. So there are a lot of steps to working out standard deviation. There definitely are, but as long as we follow them carefully and sequentially, it should be relatively straightforward. The next part we're going to look at is we want to actually examine what happens if we take the mean and subtract 2 standard deviations, take the mean and add 2 standard deviations. This is like I was showing you on the previous page, where we can assume if we had a normal distribution that within 2 standard deviations of the mean that we would get 95% of the data. Now, whether or not that is actually the case depends on the actual distribution. We're going to see if it is the case for this distribution that we've been given. So if I want to work this out, in order to actually work out this here, we're going to have to figure out this individual value. So to do this, to work out this particular value, the mean minus 2 standard deviations, we literally take the values from before. The mean, it was here, it was a value of 1.79, minus 2 times our standard deviation, which we worked out here. We approximated to 0.75, but you can write the whole value in. And when we work this out, what we end up getting is 0.2855. Please check this on your calculator as we go. Check that you're getting the same values that I am. To do the opposite, mean plus 2 standard deviations, this time it will be 1.79 plus 2 point this whole value. And what we end up getting here is 3.2945. So if we relate this back to what I was doing down here, that means that what I'm actually doing is I'm finding the values of x that are between 0.28 and 3.29. 0.28 would be located here, somewhere in between 0 and 1. And 3.29 would be located here, past our actual value of 3 that we were looking at. So in order to figure out this probability, I'm going to have to add together all probabilities that lie between those 3 sections. 0.29 plus 0.51 plus 0.16. And we get 0.96. If we relate this to what was going on before, we can see that this is actually very, very similar to our 95% which we had here, which is what we would expect. It's not exact because this information is not necessarily distributed normally, completely symmetrically, as we saw there. Alright, our last example for today. Remember our variance properties we had before? If we had the variance of a linear function, our property said that we take the gradient and square it and then multiply by the variance. So following the property here, this is the linear function 2x plus 0. So our gradient is 2. We have 2 squared multiplied by the variance of x. 2 squared is 4. Variance of x, it tells us here, is 9. So we get an answer of 36. The second one, variance of, and that should be option B. Whoops. This one here is the same as saying negative x plus 1. So our gradient is negative 1. I square the negative 1. Notice I'm putting brackets around it, so we remember that the negative is squared, multiplied by variance of x. Negative 1 times negative 1 is positive 1, multiplied by variance of x is 9. So we have an answer of 9. And that is all for today. If there is anything that you're not sure of, please make sure that you make a note and you come to talk to me about it. Thank you for watching and enjoy the rest of your probability experience.